Hi students, welcome to Max Point of View. Today we are going to understand the formation of image by a lens. This is part B of the chapter Refraction through a lens. So here this chapter is very much important. Why? Because one question will be asked for either 3 mark or 4 mark, and that too easily you can get it. So what we are going to learn from this chapter: first, differences between real and virtual images, basics of ray diagram and how to draw the ray diagram. And while drawing the ray diagram only, I am going to teach you what are the mistakes you should not do, that is done by the students commonly, how to avoid all those things and get the 3 or 4 mark easily within 2 minutes. So without wasting any time, we'll start with the concept. First, we have to learn the differences between real images and virtual images. It is very simple. Listen. So first one, okay. Real images are formed due to the actual intersection of refracted rays. What do you mean by that? See, very simple. We know this is a convex lens. So here, this is optic center and this is principal axis. So if a ray comes here, see how it goes, all those things we are going to learn, and the simple basics we have learned from part A. So part A is also very much important. So after refraction, see somewhere it is going to meet. Okay, here we are going to get the real image. So how I am telling it is a real image. Real images are formed. Okay, these are formed. So real images are formed due to actual intersection of refracted rays. So this is very much important. After the intersection of refracted rays, see these two are the refracted rays, right? So there is an intersection. That's how the real images are formed. Here when it comes to virtual images are formed when refracted rays appears to meet. There is no actual intersection. But they appears to meet. So now listen. This is optic center, principal axis. We know from concave lens, okay, it diverges away. See, these are the very much important basics. This is what we have learned in part A. Here also we are going to learn, don't worry, basic ray diagrams I am going to teach you. So in convex lens, here after refraction, they move towards the principal axis. But when it comes to concave lens, it moves after refraction, it moves away from the principal axis. So they are never going to meet. What did I tell? It appears to meet. So if you extend these lines backward, so wherever they are going to meet, there we are going to get the virtual image. Actually virtual image is not possible. So they just to make sure we are getting some kind of image which is not real, that is nothing but virtual image. Our next point, real images can be obtained on screen. It can be obtained on screen, but virtual images cannot be. Okay, these cannot be obtained on the screen. Next point, see, real images are always inverted. Okay, inverted means it is always upside down. Images will be always upside down. Object will be always, okay, upside. Okay, it will be erect. This is called erect. So if the image is like this, okay, this is called as erect, and the image is downward, facing downward direction, this is called as inverted. So real images are always inverted. Virtual images are always erect or upright, both are same. So few students will write erect and upright. That is completely wrong. It is erect or upright. These are the differences between real images and virtual images. Now we'll learn the basics of ray diagram. See, all the complete basics of ray diagram we are going to learn here also. In part A, I have told you basics of ray diagram we are going to learn here only. So don't worry about it. We are going to learn the complete basic ray diagram. Then only we are moving forward to the actual ray diagram. Now we'll learn the basics of ray diagram. Here we know this is convex lens and this is concave lens, correct? So this is optic center. For both the lenses, optic center, this imaginary line in both the lens is called as principal axis. This you should know. Okay, now listen. Here for optics, see the lens, convex lens and concave lens. For convex lens, left side it is f1 and this is 2f1 and it keeps on moving 3f1, 4f1. Okay, right side it is f2, 2f2. This you should know. Okay, but when it comes to concave lens, on the left side it is not f1 to f2, it is f2 to f2. Whatever it is there on the right side of the convex lens, that will be on the left side of the concave lens. Okay, these differences you should know. Okay, then we'll come to what is f1 and f2, all those things. See, f1 is nothing but the principal focus. This is what we have learnt in part A. Okay, so here we have the distance from the optic center to f1, assume it is 5 centimeter. From f1 to f2 it is also should be 5 centimeter. Okay, so if whatever the distance you are taking here, the same distance you have to take here, and whatever the distance you are taking from O to f1, the same distance you have to take from O to f2. Okay, so here, and why we have both the side, why we have focus, that is what we have learned in concept video, that is concept video of part A. Okay, and then here the same thing, but instead of writing f1 and 2f1, for concave lens we'll write it as f2 to f2, that side. Okay, on the right side we'll write it as f1 and 2f1. This is the main difference you should know. Now we'll talk about the rays. See, there are three possible rays. Listen, one, it can be parallel to principal axis. A ray of light can be parallel to principal axis. Then a ray of light can pass through optic center. Okay, we'll name it A, B. Okay, then a ray is not parallel to principal axis. Okay, see, these are the only three possibilities. One, it can be parallel to principal axis. Then one, it can pass through optic center. One more ray, okay, we'll assume it as C. Okay, it is not parallel to principal axis. See, if you take a ray from this point to in this direction, again it is not parallel to principal axis, correct? If you take from here to here, okay, in this direction, if it goes in this direction, again it is not parallel to principal axis, correct? See, parallel to principal axis, only one ray we can get. It can be easily seen it is parallel to principal axis. A ray can be passing through optic center in any direction. Okay, in any this direction, this direction, this direction, this direction, all those directions will considered as it is not parallel to principal axis. That's it, only three possibilities. Okay, see, if a ray comes here in this direction, okay, in this direction it is hitting here, so again compare that to principal axis, it is not parallel to principal axis. These are the three possible rays we can get for both concave and convex lens. For concave also, one parallel, one passing through optic center, and it can be anyway, it can come like this also. Okay, it can come like this also. So it is not, this ray is not, it is considered as not parallel to principal axis. We'll name them A, B, C. Okay, first we'll talk about this one, convex lens. So if it is parallel to principal axis, if a ray is parallel, this is very much important. This is what we are going to do in image formation. So you have to understand the concept properly. If a ray is parallel to principal axis, after refraction, see, this point should not touch the lens, it should touch the midpoint of the lens. After touching the midpoint of the lens, it moves towards the principal axis, it moves towards the principal axis. Where it is going to move, all those things not required for now. Okay, whenever we are talking about image formation, then I am going to teach you. For now you have to understand, if the ray is parallel to principal axis, see this line is exactly parallel to principal axis, correct? This is the principal axis, this line, okay, it is exactly parallel to principal axis. So for this ray, see, whenever you are drawing the ray diagram, it should not touch the surface of the lens, it should be middle, okay, till middle you have to draw. After reaching the midpoint only, it starts refracting. So here, after refraction, if it is parallel ray, we are talking only about the parallel ray. If it is parallel to principal axis, after refraction it passes through f2, it passes through f2, keep this in mind, okay, it has to pass through f2. Next, if it is passing through optic center, if it is passing through optic center, you just extend this one, okay, it passes without deviation, it passes without deviation, keep this in mind. Next, if it is not parallel to principal axis, see, B, it passing through optic center, if it is any ray, if it is passing through optic center, it will not, okay, deviate, it passes straightly without any deviation. And then if it is not parallel, any ray which is not parallel to principal axis, after the refraction it becomes parallel, it becomes parallel. So we see, whenever we are drawing the ray diagram, we are going to select any two rays. How many rays we have here? 3 rays. We are going to learn all the 3 cases. So one, what happens, okay, after refraction, if it is a parallel ray, okay, parallel to principal, then if it is passing through optic center, then a ray is not parallel to principal axis. What happens? All these things you should know. See, very simple. If it is parallel, it passes through f2, okay, after refraction it passes through f2. This is about convex lens. Concave, it is different case. Next, if it is passing through optic center without deviation, it passes straightly. Then if a ray is not parallel to principal axis, see, this ray, okay, this ray is not parallel to principal axis. So what happens? After refraction it becomes parallel, it becomes parallel to principal axis. So wherever these rays are going to meet, there we are going to get the real image. So whenever you see intersection of refracted ray, after the refraction, if the refracted rays are intersecting, then we are going to get a real image. If there is no intersection, virtual image will be formed, and I'll show you how to get the virtual images also. Don't worry about it. For now, these are the basics. Now we'll talk about concave lens. See, in concave lens, of if a ray, now we'll talk about a ray which is parallel to principal axis. Okay, if it is parallel to principal axis, after the refraction it moves away from the principal axis. See, this ray in convex lens, after refraction, if it is parallel, after refraction it moves towards the principal axis, that to pass through, it will definitely pass through f2. But here, after refraction it moves away from it, Next, in this case also, in concave lens also, if it is passing through optic center, okay, it passes without deviation, Then finally, a ray which, if it is not parallel to principal axis, again in this case also it becomes parallel, See here, it is, you can see it is if you extend this one, this is these 2 rays are going to meet, but in concave lens it is never going to meet. You will get to know once we are drawing the ray diagram. Now see one thing, what are the key differences between these 2 lenses? In both the lenses, if it is passing through optic center, it passes without deviation. Next, if it is not parallel, okay, in both the cases, see, this line and this ray both are not parallel to principal axis. So after refraction it becomes parallel to principal axis in both the cases. But the only difference is, if the rays are parallel in convex lens, it will try to converge. Converge means moving towards the principal axis. This is the principal axis, right? This line. So it moves towards the principal axis, and that too passes through f2. It definitely passes through you have to keep this in mind. But when it comes to concave lens, if it is parallel ray, after refraction it moves away from the principal axis. That's it. These are the basics of ray diagram. So based on these things only, we'll take any two rays and we'll draw the ray diagram to form an image. Now we'll learn one more important concept. Okay, how to calculate the size of the image and how to calculate the size of the object. So this is a very simple concept. See, principal axis, the size of the image and size of the objects are calculated from the principal axis. Principal axis will taken as a reference line. Listen, assume this is the object height. See, object is always denoted as AB or MN. Okay, XY, anything is fine. So if dash is there on them, it denotes image. If without dash, it will be taken as object. So whenever you are representing any object, you can take any two letters, but there should be no dash above them. Okay, so then it will be considered as object. So this is the object, and assume this is the image. Real image, it is inverted. Okay, and I will name it. See, for this one we are getting this as an image, right? So this will be B dash and A dash. See, assume this is the head. Okay, where is the head of the object? Here. Where is the head of the image? Here. So this, if this is A, this head also should be represented as A, but A dash should be written. Why? Because dash represents it's an image. Okay, this orientation AB and B dash A dash, this is very much important. Okay, where is the head? This is the head, right? So what letter we have? A. For the same object we got the image, right? So if this is A, this head should be A only, represented as A only, but just to differentiate between object and image, we have to write a dash. And this part, okay, again B, the same thing, right? The same thing here. So this will be B dash. Then what kind of another image we can get? Virtual image. Okay, virtual image will be always above the principal axis. Real images will be below the principal axis. Keep this in mind. So if this is a virtual image, okay, this will be like this. See, for a lens you can get only one image, one kind of image, whether it may be real image or virtual image. We are just learning the cases. Okay, so for an object, okay, any lens, you keep an object in front of any lens. Sometimes you may get real image. This is how you are going to represent. And if it is virtual image, okay, so here we are going to get it this big. So you have to represent it as A dash and B dash. Virtual images are always upside. Okay, but real images are always upside down. Upside, you should not use it is upside. It is erect. What do you call this as? Erect image. Okay, it is exactly like the object. If it is facing towards downward, it is called as inverted. Okay, now listen and see, this is about how to find the size of the object or size of the image. See, from the principal axis, this is the principal axis, right? From the principal axis till the object, till the top of the object is the size of the object. Again, how to calculate the image size? See, from the principal axis, okay, till the top, till the bottom of the image, this is this big. Object is this big, image is only this big. So if the size has reduced, that means it is diminished. See, if the size is reduced, if size reduces, it is considered as diminished. Okay, highly diminished, okay, and diminished, don't worry about this. I am going to teach you during the ray diagram. Then if the size increases, if the size of the image, see, whatever we are talking here, we are talking about if the size of the image reduces, then we call it as diminished. Size of the object cannot be reduced or increased, it is fixed. Okay, size of the image can be reduced or increased. See, if the size increases, then we call it as magnified. So what do you mean by magnified? The size of the image has increased after refraction. Okay, if it is reduced, see this bigger, compare, this is the object and this is the image, correct? So compare this size, all the size of the object and size of the image, only these two are calculated from the principal axis. So this much, compare this much and this much, the size of the image has reduced, correct? That is why this image is diminished. We call it as diminished image. That means the size has been reduced. See, this is the object and this is the image. Okay, this is a virtual image. Virtual images are always erect upside. Okay, so compare these two sides. If this is the object and this is the image, compare the sizes. See here and here, this is big, correct? So we can say the size of the image is magnified. Magnified means it has increased. Sometimes, see, if it is real image, we got to know it is real images are always formed because of the intersection of refracted rays. That means after refraction, the refracted rays should meet at a point. Assume the point is on the principal axis. Okay, here we are going to get the image. Okay, here we are going to get the image. See, how we got to know this much size? Because any two rays after refraction, they are going to intersect here. They are going to intersect here. From that point to principal axis, we have to draw a line that will be the size of the image. This is what we are going to show in ray diagram. Don't worry. Here I am telling you the meaning of what is the meaning of diminished image and magnified image, and there is one more type of image. That is what we are going to find. This is what that is. So if the intersection is on the principal axis, so the size of the image will be diminished to a point. Diminished to a point. What do you mean by this one? Very simple. Okay, well, from where we are calculating the size of the image? From the principal axis. If the intersection is on the principal axis, okay, we cannot get the image bigger. Okay, like this. Okay, correct, because it is, see, this intersection somewhere below the principal axis. So from the principal axis till this intersection, this is the size of the image. If the intersection is on the principal axis, that means the image size has been reduced to a point. So that means it is a point size image. This much, only this much big image. That we can write it as diminished to a point. This is the different sizes of images. So if the size has reduced, we call it as diminished, and if the size is increased, we call it as magnified. If the intersection, okay, there is no size, okay, if the intersection is on the principal axis, we cannot calculate the distances because it is on the, we cannot calculate the size because it is on the principal axis. Then we call it as, for these kind of images, we call it as diminished to a point. If you know this much, we can aramse start with the ray diagram. First, we'll learn everything, complete ray diagrams about convex lens. After learning everything, all the ray diagrams about convex lens, we'll move on to the concave lens. So here, first thing, draw the convex lens and principal axis, and we know F1 should be on the left side of the convex lens and F2 should be on the right side of the convex lens. That is not the only thing. The distance from the optic center of the convex lens to the F1 should be equal to the distance from the optic center of the same lens to F2. So O to F1, okay, the distance should be equal to O to F2. This is how you have to draw the ray diagram. Here what we are going to do is, we are going to keep the object in different places. The same lens, convex lens only, we are going to keep the object in different places. First, we'll keep the object at infinity. Okay, at infinity. Next, what we are going to do, so we are going to keep the object somewhere too far, not at infinity. Then what we are going to do, we are going to keep the object beyond 2f1. Then we are going to keep the object at 2f1. Then we are going to keep the object between 2f1 and f1, and then we are going to keep the object at f1, and then we are going to keep the object between f1 and optic center. So for all these different places, we are going to draw the ray diagram. That's it. So here one thing you should know, as the object is too far away from the lens, the image size will be reduced. As the object keeps on coming towards the lens, the image size will be keeps on increasing. These things you should know. There is a pattern. Okay, if you understand that pattern, I'm going to teach you all these things. So if you understand the pattern, it is very easy to draw the ray diagram. The one important thing is for the distance from optic center to F1 and F1 to 2F1, all the distances should be equal. If you follow this one, you can draw the ray diagram. Now the first case is in convex lenses, you are keeping the object at infinity. Okay, if you keep any object at infinity, okay, we will get two rays, that too parallel to principal axis, one above the principal axis, one below the principal axis. This you have to follow because this is given in the textbook one thing, then we cannot see the object. So if you see the object, we can take any two rays parallel to principal axis passing through optic center and not parallel to principal axis. But if you don't see an object, this is what you have to follow. If the object is at infinity, we will get only two rays. Both the rays will be parallel to principal axis. One is above the principal axis, one is below the principal axis. Okay, so above the principal axis we will name it as A, below we will name it as B. Okay, ray A, okay, it is parallel to principal axis. We are talking about convex lens, correct? Convex lens. So here after refraction, where will it go? It will converges towards the principal axis, correct? It will, after refraction, it moves towards the principal axis. And in the basic ray diagram I taught you, if it is parallel, it will definitely pass us through F2. It will definitely pass us through F2 if it is parallel. And if it is convex lens, it will, after refraction, it will definitely pass us through F2. In the same way, the ray B, it is also parallel to principal axis. The only difference is it is below the principal axis, correct? If it is below the principal axis or above the principal axis, the important thing is whether it is parallel or not parallel. It is parallel, right? So after refraction, it is also going to pass through principal axis. That is nothing but at F2 only. It is going to pass through F2. So now see now after drawing the ray diagram, now the size of the image is point size, because all the, see, from the principal axis, okay, from the principal axis only we are going to calculate the size of the image. If the intersection, this intersection is going to give us the reference point. In the previous slide we have learnt it, right? Intersection point, wherever you see the intersection point, from that intersection point to the principal axis, till the principal axis, that will be the size of the image. But intersection in this case is on the principal axis, so the size has been reduced. We cannot calculate the size. The size is only dot size, correct? So these kind of images we call it as diminished to a point. So after drawing the ray diagram, these three things you should write. Okay, first, position of image. Position of image. Where is the position? Where you can see the position at F2. At F2. And one more thing, see, assume, okay, this is the point. This is the point of F2. This is the point of F2. If you get the intersection here, we call it as F2. If you get the intersection here, here, in all the cases, we call it as F2 only. Okay, this complete straight line we call it as F2. If it is falling exactly on F2 or below F2 or above F2, exactly on that line, okay, we call it as at F2 only. Okay, the position of the images in all the cases will be at F2 only. If there is no rule that it has to be exactly on F2. Okay, no, it can be below F2 or above F2. In all, for all these cases, we considered as the position of the image will be at F2 only. At F2 only. These things you should know. This is not only for F2. 2F2, okay, or with this side, left side, we are getting F1, 2F1, all those, right? So all these condition will follow everywhere. Okay, you will get to know once we are drawing the ray diagram for different cases. Now, so these three things you should know. First, the position of the image. Second, the nature of the image. Do you see any intersection point? If you see any intersection point, okay, then definitely it is real and inverted. If the image is real, okay, it will be definitely inverted. So how we get to know whether it is a real image or virtual image? If you see any intersection point, okay, then it is a real image. If it is real, it is obviously inverted. So we have an intersection point at F2, so it is real image, real and inverted. The last characteristic is size of the image. So if the size of the image is always calculated from the principal axis. So if the image is on the principal axis, that means the image size is diminished to a point. Diminished to a point. All the three you should write for all the ray diagram. Any ray diagram, you write all these three properly, you will get complete mark. Complete mark. Okay. If they are specifically asking just the nature of the image. Nature means whether it is real and inverted or virtual and erect. This is the nature. Okay. If they are talking about size means if it is magnified or diminished or same size of the object. These are the three different magnification. There is nothing but three different sizes. Position we can say based on the ray diagram. For this case, position of the image is at F2. Okay, like this we are going to draw the ray diagram for both the lenses in all the cases. You have to learn properly one by one. Now the object is too far, that is at infinity. That is why we are getting two parallel lines. So if you bring it near, these two rays will be completely different. That is nothing but the next. Now we'll talk about the second case in convex lens. So when it comes to convex lens, the second case will be, see, there is no first case, second case and all, based on the position of object. Okay, we are talking about case 1 and case 2. For case 1, it was the object was at infinity. Now it is too far, not at infinity, but it is too far, which we cannot see. Okay, so in this case, if they specify if the object is at infinity, means you have to take two parallel lines. But in this case, it is not at infinity, but too far. Now for this case, you have to take these two rays only. So, okay, two rays which are not parallel to principal axis, but in one case, one ray, okay, which is passing through optic center. Okay, so these two rays you should take only when they specify if the object is at too far, not at infinity. Too far means two rays will not be parallel to principal axis, but one of the ray is passing through optic center. That is nothing but ray A. Ray B is not parallel to principal axis. So what happens? We know if it is passing through optic center, there will be no deviation. It passes straightly. Okay, next, the ray B, if it is not parallel to principal axis, what happens? After refraction, it becomes parallel to principal axis. Now after drawing these two rays, after refracted ray, where is the intersection? Do you see any intersection? Yes, there is an intersection. That means it is a real image. Okay, now from the intersection point, okay, draw the image. From that intersection point, head will be there. From that intersection, okay, a line will go till the principal axis. So this is the size of the image. Now once you draw the ray diagram, once you get the image, you have to denote the points, okay, with some letters. So for object, if you are taken AB, okay, here you have to take it as B dash and A dash, because it is inverted. The dash represents it is an image. Okay, AB became B dash A dash because it is inverted. Okay, it is facing downward, correct? So once you draw the ray diagram, these three things again you have to specify. See, in the previous case only I told you, see, in the previous case at F2 we got the intersection. Now we got below F2. If it is below F2 or above F2, anyways the position of the image we considered as F2 only. Okay, at F2, what is the position of the image? That is at F2. Okay, next, nature of the image. Nature means it should be real or virtual. Correct. It should be real or virtual. Do you see any intersection point? Yes. If you see any intersection point, that means it is real. If it is real, it will be inverted. So nature of the image is real and inverted. Then we'll talk about size. So if the object is too far, if the object is too far, the object height will be this big. After object height will be this big, but how much image height we got? Only this much, correct? So compare this big and this big nature. So this is very small. Very small is considered as highly diminished. Highly diminished. See, as the object is coming near to the lens, okay, the size of the image will keep on growing. So initially it was point size, this size image, when it was at infinity. Now it is too far, not at infinity, so it is highly diminished, only this big. Okay, so the size of the image is highly diminished. Application of case 1, that is nothing but when the object is too far away from the lens and not at infinity, too far away from the lens. Here we have two applications. First one, used as magnifying glass or burning glass. So what do you mean by this? In childhood we used to burn a piece of paper using sun rays and magnifying glass. When you keep the magnifying glass between sun rays and paper, we can easily burn it. This is one application. And why it is getting burned? Because all the sun rays which are parallel, okay, after going through the magnifying glass, it gets converged to a point. Our second application is, it is used as camera lens. It is used to photograph an object which is too far away from the lens. Our next case in convex lens. So now the object position is not too far, it is just beyond, okay, just next to 2f1, that is we considered as beyond 2f1, not behind, beyond 2f1. Okay, now you can see the object. Correct? So from the object you can take any two rays, one parallel to principal axis, one ray passing through optic center. Now ray A is parallel to principal axis, ray B is passing through optic center. Now we'll talk about ray A. If it is parallel to principal axis, what happens? This is a convex lens and it tries to converge. Converge means move towards principal axis, but where it will pass? If it is parallel, it will always pass through f2. It will always pass through f2 after the refraction, like this. Then second ray B, it is passing through optic center, then there will be no deviation. It passes straightly. So where these two rays are meeting, okay, there we are going to get the image. So what is the image size? That is also important. So now how to rectify the image size? Okay, first find the intersection point. From the intersection point, draw the image. So anyhow the intersection point is below the principal axis, it will be always inverted, correct? So object is erect, okay, it is upright, it is like upside, facing upside, but the image is facing downward. So now once you draw the ray diagram, denote the images by a letters. If you have taken object as AB, that will be B dash, A dash. If you have taken MN, that will be N dash and M dash. Anything is fine. So now once you draw the ray diagram, these three things you should write. So first, position of the image. Where is the position? Here we cannot exactly say it is not just below the f2 or above f2 or below 2f2 or above 2f2. It is between f2 and 2f2. It is between f2 and 2f2. So you can write it like that only. So position of the image is between f2 and 2f2. Next, nature of the image. Nature depends upon intersection. Do you see any intersection there? Yes, there is an intersection. So it is a real image. If it is real, it will be inverted. So nature of the image is real and inverted. Next we'll talk about size. So here compare the object size and the image size. image size is little reduced compared to object size, correct? So it is diminished. In the previous case it was highly diminished because the size of the object was this big and the size of the image was only this much. That's why highly diminished. Now it is reduced little bit, so we can say it as diminished image. So size of the image is diminished. That's it. Now we'll talk about the application of case 2. It is also very simple. It is used as camera lens. In case 1 also we used as camera lens. In case 2 also, in this case also we are going to use it as camera lens. How is it possible? How this case 2 is different from case 1? Very simple. In case 1, okay, it is used as camera lens to photograph an object which is too far away from the lens. But in this case, it is used as camera lens to photograph the object which is not too far away from the lens. This is the only difference between case 1 and case 2. Now we'll talk about case 3. Here, when the object is placed at 2f1, when the object is placed at 2f1, here the object is m and n. Here we can take any two rays, one parallel to principal axis and other passing through optic center. Which is the other possible ray? The ray which is not parallel to principal axis. All these rays, okay, basics we have learnt in the same video, in this video only, before starting any of our cases. So you can take any two rays. In one of our board exam, they have asked to draw the ray diagram using three different rays. One parallel to principal axis, one passing through optic center, one which is not parallel to principal axis. So using three rays you have to draw if they mention three rays. If they don't mention anything, using two rays we can converge, we can get the intersection. So two rays are enough. And one more thing, no one is going to, whenever I evaluate any paper, we are not going to use the scale exact, whether you have taken exact distance, same distance from optic center to f1, from f1 to 2f1, but you have to do that. We are not going to check it. We just want the ray diagram to be neat, okay, neat and perfect. And whenever we talk about perfect, we are not going to measure it, okay. We want whenever the object is placed at, okay, 2f1, where we should get the image, that is important for us, okay. So we are not going to verify all those things. For 90% of the students, you will get the exact ray diagram whenever you draw it in an exam or somewhere while practicing. You will get exactly like textbook. For few students, you will not get because of some difference in the distances. So what you can do is you can adjust it. We are not going to verify in the board exam. So don't worry about it. Now for this object, when the object is placed at 2f1, what are the two possibilities? One ray is parallel to principal axis, one is passing through optic center. If it is parallel to principal axis, what happens? It will converges at f2. You see, whenever it is parallel to principal axis, it is always going to cross, okay, it is always going to pass through f2. Keep this in mind. Next, if it is passing through optic center, what happens? Without deviation, okay, it passes. So where these two rays are intersecting, can you see any intersection? Yes, these two rays are intersecting at some point, correct? At that point we are going to get the image. How is the image? See, compare the object and image. Object is upward and the image is downward. So whenever we see any object or image, anything in upward direction, we call it as erect. We call it as erect. See, the object is upside, right? We call it as erect, okay, or you can call it as upright. Erect is nothing but upright. Both are same. When it is downward direction, we call it as inverted. The image is inverted, correct? So here the object is mn, the image is inverted, so it is n dash and m dash. That's it. So once you draw the ray diagram, these three plus one application you should know. Okay, first one, position of the image. Where is the position of the image now? Exactly below 2f2. So when the object is at 2f1, okay, image will be at 2f2. What is the nature? Obviously, if you see any intersection, that is real and inverted. Then what is the size? I told you when the object is kept at 2f1, okay, the size of the object will be equal to the size of the image. This is the only case we will get these kind of magnification. Magnification means comparison of size of object to size of image. That is nothing but magnification. Those numericals we are going to solve. Don't worry, first we'll understand how to draw the ray diagram. So once you get all these characteristics, the important thing is application. So where we can use these kind of lenses. Telescope, why not the normal telescope? The difference is very simple. In normal telescope we will get inverted image, but in terrestrial telescope, this telescope will again, once you get the image as an inverted, it again convert to erect means upright. The image will be upside down, so that we are, for any observations we can use it aram se. So what is the only application of terrestrial telescope? It is used to get the image of terrestrial object as an erected image, not inverted image. Now we learn everything about case 4. Here the object is kept between 2f1 and f1. So what are the possible rays we can expect? One parallel to principal axis, one passing through optic center. Any two rays we can take out of 3. Which are those 3? We are learnt in the beginning of this chapter. Any two we can take. So now if it is parallel to principal axis, what happens? It will passes or converges through f2, correct? Then if it is passing through optic center, what happens? Without deviation, it passes straightly. So where these two rays are going to meet, do you see any intersection? Yes, there is an intersection, correct? So if you see any intersection, that means it is a real image. Now where you are going to see the intersection? From that point to principal axis, you have to draw the image. Now the object is taken as m and n. The image will be it is inverted, right? So it will be n dash m dash. Now once you draw the ray diagram, these are the important things, characteristics you have to write. Position of the image. Where is the position of image? It is beyond 2f2, correct? It is beyond 2f2. That means it is crossing 2f2, correct? Next, what is the nature? Do you see any intersection? Yes, if you see any intersection, that means it is real and inverted. Then size. See, compare the object size and the image size. Image size is comparatively bigger to the object. So the image size is magnified. The image is magnified. So these are the natures. Now we will talk about the application. So what is the application of these kind of lenses? When the object is between, the same lens, but where is the position of object is different. Based on that, different applications are there. When you place an object between 2f1 and f1, the application is very simple. It is used as cinema and slide projector. Here also we are going to get erect image. In previous case we used terrestrial telescope. In that case also we are going to get the erect images. To see it properly like this, if the image is upside down, it will be very difficult for the observation, correct? So these lenses will make it as erect image, erect. So what is the difference between terrestrial telescope and cinema or slide projector? Here in that previous case, terrestrial object, the image was not magnified. Here it is erect as well as magnified. So these are the key differences you should know case by case. So in this case we are going to get erect image only, but magnified image. Keep this in mind. Now we learn about case 5, when the object is placed at f1, exactly at f1. So here the object is mn. When the object is placed anywhere, so one parallel ray we have to take, one passing through optic center. See why we have to take only these two? Because it is mentioned in the textbook. You can take these two, or you can take one more ray which is not parallel to principal axis. You can take any two rays. We're going to get the same image only. When one ray is parallel to principal axis, what happens? We know it definitely passes or converges through f2. That is done. Then if it is passing through optic center, it will passes without deviation. Now we don't see any intersection in this case, correct? It is almost like parallel to each other, but definitely they are going to meet at infinity. Definitely they are going to meet at infinity somewhere, we don't know. Okay, there is a small change. Okay, it's not exactly parallel. When you keep on extending these two rays, it is definitely going to meet at some point, we don't know, we assume it as infinity. Once you draw the ray diagram here, anyhow we cannot see the intersection, so we cannot draw the image. So here, once you draw the ray diagram, these are the important things. Characteristics, okay, we should know. Position of the image at infinity. Position of the image is at infinity. Then nature, we know it is going to somehow, it is going to meet, because these two rays are not parallel, so it is going to meet. Definitely it is real and inverted. Then size, see, it is going to meet at infinity, right? So highly magnified you can write, or else you can write it as infinite size image. Infinite size image. So once you write all these characteristics, the important thing is application, where we can use these kind of lenses. When the object is at f1, where we can use it, we can use this one in collimator of spectrometer. What is this collimator and spectrometer? See, this is the main difference between, so learning from the textbook and learning from teaching. Okay, whenever we teach, we'll explain all those things. That is why these kind of videos are useful. So what is spectrometer? Spectrometer is a device which will, okay, splits, okay, the color. If you give any color, white color, okay, it should not be monochromatic. Whenever we give any color, okay, which is not monochromatic, it splits the color into its constituent colors. That is the meaning of spectrometer. Then what is this collimator? Collimator is a device, is a part in spectrometer which will convert diverging beam of light. Whenever you give diverging beam of light, it will convert into parallel beam of light. Okay, to get to parallel beam of light. Our last case in convex lens. Here the object is kept between f1 and optic center. When this is possible, this is very much important case, you will get to know why. Okay, so when the object is kept between f1 and optic center, what are the two possible rays? One parallel to principal axis, one passing through optic center. If it is parallel to principal axis, what happens? This is what we have learned from all the cases. It will definitely converges, okay, through f2. If it is passing through optic center, without deviation it passes. Now compare the rays. Now definitely these two are not parallel. If these two are not parallel, they are never going to meet. If they are never going to meet, we are not going to get the real image. Then what kind of image we are going to get? Virtual image. Where we are going to get the virtual image? So extend, okay, extend those refracted rays, okay, backwards. If you extend those refracted rays backwards, where they are going to meet, okay, definitely it is between 2f1 and f1, okay, somewhere, okay, between 2f1 and f1, there we are going to get the image. This image is not upside down. This image is not upside down. That is nothing but it is not inverted. This is erect, and we know there is no intersection. That is why it is a virtual image. Now these important characteristics we should write. Position of the image on the same side of the object. Where is the object? This side, on the left side of the lens, correct? The image will also be on the left side, so position of the image is same side on the object. Next, nature, we cannot see any intersection, right? So it is virtual and erect. Then size, compare the size of the image and size of the object. It is magnified. So these are the characteristics. Then what is the application of these kind of lenses? This is used as a reading lens. In many of the questions, whenever you see reading lens, it is definitely convex lens. Okay, convex lens. In the convex lens, where is the position of the object? It is between f1 and optic center. Keep this in mind. Whenever they say specify reading glass, this image you should remember. Okay, so the application is, it is used as reading lens. See, sometimes in magnifying glasses or reading lens, that is nothing but magnifying glasses, okay, or simple microscope. Why we have to use it like this? To get the magnified, virtual and magnified image of tiny objects. When the objects are very tiny, Okay, when the objects are very tiny, we use these kind of lens. We have to keep the object, okay, we have to keep the object between f1 and optic center, then we'll get magnified virtual image. This is the application. Now we have learned everything about all the cases of convex lens. In the same way, we'll learn everything about concave lens also. Here, drawing the ray diagram is not only the important thing. Ray diagram, all the characteristics and applications of different cases. See, based on all these things, for students who are planning to get more than 75, more than 70, applications are also very much important. See, it can be asked in any way. Okay, it can be asked in MCQs. It can be asked as in a ray diagram. Okay, draw the ray diagram and mention it application. Anything is possible. So always learn everything, be in a safer side. When it comes to concave lens, we have only three cases, that is case 0, case 1 and case 2. Why we are taking the first case as case 0? Because in case 0 we don't have any application. Okay, first we'll learn everything about concave. See, the basics we have learnt. When it is not parallel to principal axis, when it is parallel to principal axis. If you don't know, in the same video, in this video only, in the beginning we have learned the basics of these rays. The first that you need to understand, then this will be very easy. Now listen, when we have a concave lens, the difference between concave and convex, on the left hand side, for convex lens, for the left hand side we had 2f1, 2f1, 2f2, okay, like this. On the right side, for a convex lens we had f2, 2f2, but when it comes to concave lens, everything is opposite. On the left side we have f2, 2f2, on the right side we have f1, 2f1. This is very much important when you are drawing the ray diagram. Once you know this one, so the next thing is, we have first case, it is nothing but case 0, when the object is at infinity. When the object is at infinity, only two possible rays we have, both will be parallel to principal axis, exactly like this. We know if it is parallel to principal axis, okay, in convex lens, it will converges, correct? But in concave, in this case, okay, concave lens, it will diverges. So how we are going to get the image if it is diverging? If it is intersecting, we can easily say from that point to principal axis, that is the image. If it is never going to intersect, then how we can get the image? After refraction. After refraction, so the extend backward the refracted rays. Those are the refracted rays, right? Extend it backwards, where they are going to meet, there we are going to get the image. Now, once you draw the ray diagram, okay, we have to write the characteristics. Position of the image is at f2. Then nature, we cannot see any intersection of refracted rays, right? So it is virtual and erect. Virtual means it is not real image. Erect means upside. It is not inverted. Erect means upside, like this. Okay. Next, what is the size? Size, it is exactly on the principal axis, right? So if you extend it backward, the intersection is exactly on the principal axis. All the images are calculated from the principal axis. So if it is exactly on the principal axis, the image size is diminished to a point. Diminished to a point, or else you can write it as point size image. Point size image. So it doesn't have any application. Our case 1 in concave lens. So once you draw the concave lens, the important thing is left side it is f2 to f2. Right side it is f1 to f1. That is very much important. Now here the object is too far, not at infinity, exactly like convex lens only, not at infinity, okay, too far away from the lens. Then one ray will not be parallel to principal axis. One ray will be passing through optic center. We know after, if it is not parallel to principal axis, when it comes to concave lens, it becomes parallel. Okay, in both the lenses, if it is not parallel, after refraction it becomes parallel in both the lenses. Here we are using concave, so if it is not parallel, after refraction it becomes parallel. Then if it is passing through optic center, okay, it passes without deviation. Now, do you see any intersection? No. Then how we are going to get the image? Extend the refracted rays backward. We extend the refracted rays backward. Where they are going to meet, there we are going to get the image. So if you take object as m and n, the image will be m dash and n dash. Why not n dash, m dash? In all the convex lenses we used to write n dash and m dash because it was inverted, but here it is not inverted, it is erect. So object m and n, the image will be m dash and n dash. Once you draw the ray diagram, these are the characteristics you should write. Where is the position of the image? It is at f2. Okay, in the previous case it was exactly at f2, the point on the principal axis. Now it is above. If it is on the principal axis or above or below f2, we consider as the position of image is at f2. Then once you write this one, the next thing is nature. Nature, see here we are not getting proper intersection, correct? We are extending lines and we getting the intersection. Without extending, we never get intersection. So it is virtual and erect. Size highly diminished. Okay, object is too far. Okay, object is too far, the image is only this much, correct? So it is highly diminished. Then once you write all the characteristics, what is the application of these kind of lenses? Very simple. This is used in, okay, this is used as Galilean telescope. Galilean telescope. What do you mean by Galilean telescope? Nothing but, see, in Galilean telescope we have both the lenses, convex and concave. Why we have to use both the lenses? See, in convex lens we'll get the image, but in image will be inverted just to get the erect image. Okay, whatever the image found by the convex lens, we have to erect it again. So we are going to use both the lenses. So very simple how to write. It is used as Galilean telescope to get the erect image. This is what you are going to write. All the explanation just for your understanding. Now our last case, that is case 2 in concave lens. So in concave lens we have only 3 cases, case 0, case 1, case 2, that's it. But in convex only we have so many cases. Now listen, in concave lens, very important thing, f2 to f2 on the left side, f1 to f1 on the right side, very important. Next, so here the object is not too far. Okay, in first case it was at infinity, second case, okay, case 1 it was too far, in case 2 it is at finite distance, okay, it is beyond 2f2. Okay, now in this case, what are the two possibilities? One parallel to principal axis, one passing through optic center. If it is parallel to principal axis, what happens in concave? It will diverges, correct? It will diverges. If it is passing through optic center, without deviation it passes. Here we are never going to get the intersection. So what we can do? Extend the refracted rays backward. Where they are going to meet, there we are going to get the image. So once you draw the ray diagram, these are the characteristics you should write. So first one, position of the image. It is between f2 and optic center. Next, according to the diagram, then what is the nature? No intersection, no proper intersection. We made it intersect, right? So no proper intersection. It is virtual and erect. Size diminished. Compare the object height and the image height. It is diminished. It is reduced. Correct. So these are the characteristics. Now we'll learn the application where these kind of lenses are used. These kind of lenses are used in spectacles. Okay, spectacles. Okay, for short-sighted persons, for myopia, where the person can see near objects, not the far objects. In those cases, for those people, okay, it is used in spectacles for short-sightedness, or you can write it as myopia. So these are the cases and their applications. Now we'll learn the differences between convex lens and concave lens. So here all these data you already know. So for a safer side we are going to learn. That's it. So first, see, when we talk about convex lens, okay, here we are going to get virtual image as well as the real image in convex lens. But when it comes to concave lens, only virtual image is possible. And one more important thing, see, whenever they talk about image, virtual image, see, in convex lens, we know we are going to get virtual image, correct? In concave lens, it is always virtual image. Assume there is a question, okay, related to virtual image, and the lens is not specified. Which lens they have used. How we are going to identify whether it is convex or concave? Very simple. If the image is magnified, it is always convex. Because in concave lens we are never going to get the magnified image, it is always diminished. If it is virtual and magnified, convex lens, If it is virtual and diminished, it is concave lens. Keep this in mind. So next point, here in convex lens we can get diminished image, same size image and magnified image, but in concave lens it is always diminished image. Here the image can be inverted or upright, but when it comes to concave it is always upright or erect. You can write it as erect. So these are the differences. Now we have learned all the complete ray diagram. Once you learn all these things, directly go into the theory solution. After that, sign conventions and numericals, all those things are very much important. So I believe you have understood everything. Whenever you get a silly doubt, just rewind back and watch it. You will definitely understand everything. So drawing the ray diagram is not only the important thing. Okay, drawing the ray diagram, characteristics and application, everything is important. Practice, you have to keep on practicing, and keep one thing in mind, while correcting your paper, will not keep the scale and measure it. Okay, need a ray diagram. Whenever you are drawing a ray diagram, you should use always pencil and scale. Okay, all the rays should be very straight. Okay, it should not be slant or curvy. All these notes, if you use it properly, definitely you will get the complete marks. Thank you.